Hey guys, welcome back to Extreme IE. In this video series, we're going to take a look at EIGRP packet types. Now, for the most part, you're not generally going to need to know all of the different packet types that EIGRP is sending off the top of your head all the time. But where you are going to need to at least understand them is when you're in a troubleshooting scenario, meaning maybe you're running a packet capture, or maybe you're doing a debug of some kind, and you need to actually understand what's going on under the hood in order for you to actually see what's going on in EIGRP. So let's have a look at them. So EIGRP is going to run a 32-bit header, and here's an example of what the EIGRP header is going to look like. Now, I haven't listed all of the fields. We'll generally talk about at least some of them throughout the series of the video. These are the ones that I want to outline now, and we'll get to the flags probably in the CLI of this video. We'll talk about the TLVs a little bit later on. But again, here's an idea of what the EIGRP header looks like, and it's going to be 32 bits. Now, this is going to be 32 bits, and each of these fields are always going to add up to 32 bits. So in other words, the version, the opcode, the checksum, you can see these are essentially next to each other, so they all equal out to be 32 bits. So the version number is generally going to define what version of EIGRP we're running. Now, in the old days, in like version, I think it was like 11 code, this was version 0, and then we went into version 1, and I think currently we might be running version 2. I think all the CLI, all the versions of code that I have, which are 15.2, 15.6-ish, I think, these guys are going to be running version 2 of EIGRP. And you always want to make sure that you're on the latest version, because that's going to be the one that has, you know, essentially whatever enhancements or fixes that Cisco has put out. Generally, this is going to be just based on whatever version of code you're running, and for the most part, in today's day and age, you're not going to be running previous to version 2, especially when you first take a device out of the box. If you're running in a really old router, you may find that you're in an older version of EIGRP. Now, the opcode is going to be this numerical value, and it's going to define what that packet is. Now, in newer versions, it will actually say them together. So in other words, you'll see something like hello, and then in parentheses here, you'll see the opcode of 5, or you'll see, you know, an update packet, and you'll see in parentheses, you'll see the 1. You know what I'm saying? So it's a numerical value here that's going to define exactly what type of packet that is. And I'll get into these in the next slide, what each one of these are essentially doing for us. But this is how you're going to see it in a packet capture, usually. Now, if you are in a scenario where you're only seeing the opcode of a specific number, this is where knowing this information comes into play. If you see an opcode of 5, you need to know that it's a hello packet. If you see an opcode of 1, it would help you to understand that, oh, you know, EIGRP is sending update packets, okay? Now, the checksum is going to be a value that we use to validate the actual integrity of that packet. So when we see this checksum value, we're putting it into the header so that we can ensure that the packet is not corrupt, that it's actually the right packet, if you will, all right? Again, it's validating that integrity of the packet that we're actually receiving, okay? Now, the sequence number and the acknowledgement kind of go hand in hand. So let me quickly explain RTP for a quick minute. And I'm not talking about, you know, RTP North Carolina. I'm talking about RTP, reliable transport, just say trans protocol, okay? So reliable transport protocol, I know that writing is horrendous, but I think I have it written out nicely on the next slide. So reliable transport protocol is Cisco proprietary protocol that actually ensures the reliable, hence reliable, delivery of packets. So what happens is every time we send a packet that requires an acknowledgement, we are going to go ahead and we are going to increment this sequence number. So I may send you 2 packets, and so that packet may be, you know, packet number 1, packet number 2. I'm going to increment this sequence number. What's going to happen is that once I receive the last packet, and we're going to dictate that by the flags, once I receive the last packet and I know that, hey, this is the last packet that we're receiving, what's going to happen is that I'm going to go ahead and I'm going to send this acknowledgement, okay? Now, this acknowledgement is going to contain the sequence number to the last packet that I received. Okay, and that's going to let my neighbor know that, hey, I received that last packet. And this is going to go, this acknowledgement is going to get sent unicast to that particular neighbor. So if I have R1 and R2, R1 sends me a whole bunch of packets here. And once I receive the last packet, R2 is going to send me that ACK packet, and it's going to contain that sequence number that I received. Okay. Now, lastly, the autonomous system number in EIGRP has to match in order for us to actually form an adjacency. So what happens is I'm actually going to transmit that autonomous system number inside of the packet header so that EIGRP knows whether this is the right or the wrong autonomous system number. If it doesn't match, again, we cannot form an adjacency. So this is kind of the packet header. This is kind of what the header is going to look like, or I should say the different fields when we jump into a packet capture. We're going to see all these different fields inside of the packet. So now let's talk about the actual types of packets that we're going to see. So first, we're going to see the hello packet. Now, the hello packet, when we go in and we say router EIGRP, so you say router EIGRP, and we say 12 for our AS, and I go in and I say network, and that might be 10.1.1.1, and I say 000 all the way across the board, and I enable EIGRP on this interface. What's going to happen is I'm going to start sending out multicast packets to the address 224.0.0.10, and this is going to be used for our neighbor discovery. So we're going to have a neighbor discovery process where we use this multicast address to go out and actually start trying to see who's out there. Am I alone in the world? Who else is out there? Let's form an EIGRP adjacency. All of our devices are going to start doing the same thing. Once we receive each other's hello packets, we're going to start to actually form an adjacency. And we'll go through the actual process in just a few minutes when we look at a packet capture in the CLI. So the first thing that we use these hello packets for is to actually establish this adjacency. But we're also going to use them to maintain the adjacency. So every X amount of seconds, and the reason why I say X amount of seconds is because it's going to depend whether you've modified them, whether you have a fast link like Ethernet, a gigabit, or whether you have a slow link like a serial interface or T1 interfaces. All these interfaces are going to be different. They're going to have some different timers, slow based on fast, and we'll get into those in the operational video. I don't want to waste time talking about them here. Point is that we're going to send out these hello packets to maintain these adjacencies. They're going to have an increment where they get sent out, and they're going to typically go multicast to actually ensure that we still have an adjacency. Now, you may notice that the opcode here to a hello packet is the same opcode to an ACK packet. The reason why that is because an ACK packet is simply a modified hello packet without any data. So the hello packet is going to contain all those different fields that we talked about. It's going to contain the autonomous system. It's going to contain the version. It's going to contain all that kind of stuff. And again, we'll see that in a capture. The ACK packet is going to just contain that sequence number. And again, the reason is because we have reliable transport protocol. We have RTP running, and the idea is that we have this reliable delivery of packets. So based on the diagram that I have for you guys here, R1, R2, and 3 all form an adjacency by sending these hello packets. Okay, that's essentially step one. Now, router 2 sends an update, and all these guys are going to send updates based on what they've been told to advertise, but now router 2 sends an update, okay? So this is kind of step 2 in the process. So let me just jot this down here. So this would be step 1, this would be step 2. So router 2 sends an update. That update is going to go out to his neighbors. So we're going to see updates come in to router 1 and router 3. Now, step 3 is essentially routers 1 and 3 are going to send out an acknowledgement packet, or this ACK packet. They're going to send it out, and this is always going to be unicast. Is it in here? Yes, I think. Here we go. Unicast. So these guys are always going to unicast it back to the actual address, the sending neighbor where they received it. So if router 2 sent out an update from that interface, router 1 and router 3 are going to send their ACK packet back to that particular interface. And so this is kind of the three-step process that EIGRP is going to take when we are forming an adjacency. So this hello packet's going to go out to 224.0.0.10. It's going to establish that adjacency. Then we're going to see the updates, and I'll get to what those are in a second. We're going to see an update go out, followed by an acknowledgement packet. And again, this acknowledgement is simply a hello packet without any actual data in it. It's just going to contain that sequence number, okay? Now, the update packets are what we are going to use to actually build the EIGRP topology table. That's a terrible rectangle. So the EIGRP topology table, you can essentially make this the EIGRP database, if you will. All of the routes that we're receiving, all the updates that we are receiving, the routing updates, we are going to put into the topology table, and we're going to essentially calculate our metric value. Once we have the best route or the best next hop, we're going to go ahead and take these guys, and then we're going to go ahead and put them into our routing information base, or our routing table, or RIB for short. So these update packets are going to come in essentially right here. These updates are going to come in, they're going to land in our EIGRP topology table, and that's how we actually compute where we're actually going to go as the best next hop for that route. Okay, if routes don't land in the topology table, they're not going to ever hit our routing table. We'll talk more about that when we get into the general operations. So these guys you're going to see have an opcode of essentially 1. Now, these next group of packets we're going to talk more about when we get into the stuck in active problem in EIGRP, but I'm going to essentially give you a basic description. So let's say that we have a LAN segment here off of R3, and let's say that R2 has, let's say, a few more routers hanging off, okay? Router 1 knows, because we had not just the update here from router 2, but we also had updates from router 2 and router 3. So router 1 knows that if he wants to get to this LAN segment here, he has to come down this way, essentially to router 3. Now, something happens where either this link goes away, or this link goes away. Bottom line is that router 1 has lost reachability to this LAN segment here. He no longer has it. What he's going to do is he's going to send out a query packet, and this query packet is going to be a multicast query packet that says, hey everybody, listen, I had this network, I had this successor, and now I've lost it. This only happens if we do not have a feasible successor. What a feasible successor is for lack of a better term, it's basically a backup route. It's basically, you know, if R2 had another link, let me just pick a, if router 2 had a backup link coming down this way directly to router 3, then maybe router 1 would have had a successor or a feasible successor going down to router 2. So what would happen is that router 3 would be the successor, and router 2 would have been the feasible successor, okay, the FS, if you will, okay? But this isn't here. So router 1 now sends out these query packets to say, hey, I've lost reachability to this route. Does anybody know how I can get there? Okay, now, router 3, because he doesn't have any other connection, remember this isn't here now, this was just an example, router 3 doesn't have any other connection, and this link, this network is gone. What router 3 is going to do is router 3 is going to respond with a reply packet. He's going to say, nope, have no idea. Router 2, on the other hand, is going to not say anything. He's going to say, hey, by the way, guys, I'm looking for this route. Do you know? You know, router 4 is going to say, oh, hang on a second, let me see. He's going to ask this guy, which could be router 5. Router 2 is going to send a query packet in this direction and ask router 6. And however many routers you have going down the line, these guys are all going to go ahead and ask their further in neighbor. We will only send a reply once we have validated that, nope, we don't know how to get to this particular network. So that's what the reply packet is essentially going to be. The problem with this, and again, I'll get more into it when I talk about active, the problem with this is that if this router's having a problem and he never responds to router 4, well, that means that router 4 is never going to respond to router 2. That means that router 2 is never going to respond to router 1, and that means we go into what we call an SIA process where it's stuck in active, because right now this process is called active. When we lose a successor, and we do not have a feasible successor, the route goes into active. So now what's happening is that router 1 is not getting a response, and so part of the active process is that router 1 is going to reset this adjacency between router 1 and router 2, but router 1 and router 2 don't have an issue. Okay, router 2 is perfectly fine, and we have a perfectly good adjacency between router 1 and 2. These links are fine. These links are fine. Suppose the problem is here. Maybe we have some kind of saturation or something going on R5, and network engineers are already dealing with that. Maybe that's the reason why we lost this particular link. Who knows? You know, the problem is that now we're going to reset this link between router 1 and 2. And so what we did was we implemented an SIA query and an SIA reply. What essentially happens here is that after the query packet is sent, halfway through the active process, router 1 is then going to send the SIA query and say, hey, listen, you haven't responded with a reply packet, obviously because we know that router 2 is asking his further down neighbors. But router 1 says to router 2, hey, listen, I'm going to send you an SIA query and say, you have not responded to my original query. Are we okay? Is everything okay between us? Router 2 will respond with an SIA reply, and he'll say, yes, listen, don't reset the adjacency between us. Don't kill this link. We are just fine. The problem is these yo-yos down further down the link. Okay, so these are the different packet types that we're going to see, and let's go ahead and let's dive into a packet capture in the CLI, and let's actually watch it happen. Okay, guys, so let's actually jump into the CLI here. What we're going to do is we're going to have, let's grab a pen. We're going to have a simple adjacency here between router 1 and router 2. We're going to redistribute our loopback addresses, and we're going to take a look at some of these different packets that we actually have going on. Now, you can see that I already have a packet capture running, so let's go ahead and let's actually filter this out. We don't have EIGRP running, so let's just go ahead and we'll say EIGRP. And that'll filter out any of the packets that we don't want to see. So let's go over to the CLI. And let's get EIGRP running. Now, the first thing I want to show you actually is a debug. So I'm going to say debug EIGRP packets and hit the question mark. If we want to actually see, based on the CLI output, if you wanted to actually see the sequence number, the flags, all those kind of different pieces, you would go ahead and you would enter in those various different pieces that you want to see, okay? Now, the thing is that a lot of people that I know come in and sometimes say debug EIGRP packets because they don't understand what all these different packets are. I don't recommend that you do that, because if you say debug EIGRP packets and you have a lot going on, it's going to get very, very confusing very, very fast, because you're going to have all these different packets going on back and forth. Understand your packet types. Again, in troubleshooting, this is where we need this so that we know essentially what we're going to look at. Now, for me, what I'm going to do is I'm going to debug my hello. I don't need my reply. I need my ACK. And I want to take a look at my update. And these are the packets that essentially I'm going to debug, because all we're doing is we're debugging a basic adjacency here. We'll go ahead and debug the query and the replies when we look at the stuck and active and that in that video. But here, all we really need is our hellos, our updates, and our ACK packets, because that's all we're looking for. So I'm going to say config T, and actually what I want to do over here on router 2 is I'm going to say debug IP packet, and I'll show you why I do that in a minute. So let's go over to router 1. Let me say do show IP interface brief E assigned. And what we're going to do is enable EIGRP on this interface, our E00. We're going to at some point say redistribute connected, and we're going to watch those updates come in. But for now, let's just say router EIGRP. We'll go ahead and have our autonomous system be 12. And we haven't sent anything yet, right? We have not actually sent, if we go over to my packet capture, we haven't sent any packets yet. Packets aren't going to get sent until we actually enable it on an interface. So I'm going to say 10.1.2.1. We'll go ahead and enter in all zeros because we only want it on that one interface. And what we're going to see is, boom, we're going to see the sending of hello packets, right? Now, it lets us know that we're sending a hello packet. Here's the sequence number is essentially 0. Lets us know the interface that it's going out. It lets us know the autonomous system number. Again, all those fields in the actual packet, and it lets us know the flag. By the way, I did leave this out of the theory video. The flags are important when you're dealing with troubleshooting. They're going to be a 32-bit value, and essentially they're going to let you know where you are in the adjacency, if you will. So 0 essentially means null. If we see a 1, that's the initial update that we're getting in. So for example, if I see an EIGRP adjacency flapping, generally if I see a peer reestablish itself and it's repeatedly doing that, we would call that EIGRP flapping. That means that we've already established an adjacency, and yet my neighbor is now getting in a flag value of 1, which is the initial update. You'll watch this change. You'll see this change when we establish an adjacency. Now, the thing is that with this debug, if I say do on all, we're going to turn this back on in a minute. It doesn't tell me whether I'm using multicast or unicast, right? I mean, let's say that I'm forming an adjacency between router 1 and 2, and these guys are in different data centers, and maybe there's a firewall in between that only allows EIGRP. I don't have, telnet or SSH access. I don't have the ability to go in and actually see what the other engineer has entered, and he's gone off to lunch, but I need to get this finished. I don't have the ability to see why I'm not forming an adjacency. Right now, all I see is that I'm sending hellos, but I'm not receiving any. right? Or vice versa. What I can do is the debug IP packet command is actually going to give me this output, where it actually shows me the source of the traffic that I'm receiving. So in my case here, maybe I would see on router 1 that I'm sending out these hello packets, but I'm not receiving, any hello packets. Or maybe I'm receiving hello packets from router 2, but I'm still not forming an adjacency. What's the reason? Well, maybe router 2 is talking in unicast and I'm talking multicast. I would be able to see that in the debug IP packet output, because it lets me know the source is going to be 10.1.2.1. It lets me know the Ethernet interface that I'm essentially trying to, or sending out this packet, or receiving, I should say, is going to be on Ethernet 00, and it tells me the destination address is 224.0.0.10. So it lets me know that this is a multicast packet, okay? And that's important for us to know. So you can either use the debug IP packet or you can use the debug EIGRP packets, but just be aware that the EIGRP debug won't show you everything. You have to sometimes go elsewhere. So let's say do debug EIGRP packets, and we're going to do the hellos, the ACKs, and the update. And let's head over to router 2. Actually, before we do that, let's go over to router 1 for a second. Let's go to packet capture rather. If I take a look at this packet capture and I expand out the Cisco EIGRP field, you can see that we see all those fields that I said we would. So we see the checksum value. It tells us that this is correct, so we know that this packet it's not corrupt, it's a valid packet. We see the version number. Remember I said that in current versions it's going to be version 2. We see the hello. So in this packet capture, like I said, it lets us know that this is a hello packet, and it's an opcode of 5, so it lets us know that. If you forget the opcodes, you can always just go back to your packet capture. The sequence number is 0, the acknowledgement is 0. We're not sending any acknowledgements. We're not worried because right now we're only trying to form an adjacency via the transmission of hello packets. So the flags are 0. We're not worried about anything. And here you go. It lets us know what the different values are going to be in the flags if you want to check those out. And it lets us know the autonomous system number is 12. Okay, so let's go back to router 2. We'll say config t router EIGRP 12 network 10.1.2.2 all zeros. What we should see here is if we scroll down, in theory, what we should see is we should now see that we have some hello packets go back and forth between router 1 and router 2. So here they are. So you see router 2 here, router 1 here, and we should see that we have some update packets. So remember I said that we're going to see the update packets followed by ACK packets, and this is exactly what we're going to find. So let's take a look at this. Let's take a look at this update packet. So you can see here inside of the update packet, we see that the flag is going to be set to 0.1. Let's actually head over to router 1 and see if we can find that. Let's say do on all. We should see somewhere in here, we should see a flag of 0.1. So here we see the flag set to 0.1 because we received the initial update. So again, sometimes if you see an EIGRP neighbor flapping and you see that we're receiving the flag as 0.1, this is the initial update that we're receiving, and you can see that in the packet capture here. It lets us know that this is the initial update. So you'll see here that this here the init value is going to be set to 1. All right, but again, lets us know the version, lets us know the opcode, lets us know that this checksum is correct. The sequence number essentially is 1, so we'll take a look at that in a little bit. And let's go down here and let's see this hello packet. You can see that the acknowledgement here was set to 1. So here in the update packet that was sent from router 1 to router 2, that sequence number was set to a value of 1. If we go take a look at the ACK packet that was sent from router 1 back to router 2, you can see that the acknowledgement was set to 1. So this is how we have this reliable transmission of update packets between our particular devices. Okay, so this is how we transmit RTP. This is how it works. So the sequence number was set to 1. Now we go down and we see the acknowledgement has actually flipped and set to 1. The flag has gone back to all zeros, right? Because we've already received that initial update. Okay, so we go down here and we just see now that these are just regular hello packets. We don't see anything different. We don't see any of these values in bits set. So let's actually go, we'll click on this last packet here, and let's actually go and redistribute some packets or some interfaces here. We'll just say redistribute connected, and we'll send in our loopback addresses. So let's go back to our packet capture here, and we should see that router 2 sends an update. So here's the update that router 2 sends. Let me actually stop the capture so it doesn't continually scroll on us. So we see router 2 actually sent an update. So we see the checksum here is correct. And if we go down here, we see all of these external route values. So here, router 2 is letting router 1 know here I have all of these different routes. Okay, here's my here's the length, here's the external route, here's the destination, here's the prefix length. And you can see that we sent in these updates. Now the sequence number here that we sent was essentially 3. So what we should see in the ACK packet, so when I take a look here, let me just scroll up just a bit. So this packet here was sent multicast out, this update. Router 1 should be sending an acknowledgement of 3. And again, it's just a bare bones hello packet. It doesn't have anything set, but it does have that acknowledgement. Here was the sequence of 3 and said, here's the sequence number that I'm sending you with all of these values. Router 1 responds with that same sequence value, okay? And that's how essentially EIGRP is going to work. Now, if we go over to router 1, I don't know if did we turn off the debug? I think we may have. Yeah, we did, do on all here. So let's go on to router 2, and we'll say do debug EIGRP, and we'll just say updates and ACKs. EIGRP, I forgot packet. So we'll just do the updates and the ACKs. We don't want to do the hellos because we're not worried about them anymore. Let's go ahead and say redistribute connected, and what we should see is we should see router 2, let's say do on all, we should see router 2 receive these updates. So he says received an update. The flag is essentially set to 0 because this is not an initial update anymore, and we can see that we are queuing the ACK packet, and then we're going to go ahead and send that ACK packet. So this is essentially the same process that we would see in our packet capture with the transmission and the receiving of the ACK packets, the update packets, and these hello packets going back and forth between EIGRP, okay? Now, I will get to just one quick, let me just go back into this debug here. So debug EIGRP packets and hit the question mark. We will get into debugging the queries and the reply in the stuck and active videos. We'll get into debugging the stub packets when we talk about EIGRP stub areas. But again, at a high level, these are your different EIGRP packet types that you should be aware of and know pretty well.